Hello viewers, so welcome back to the course. So this is the lecture number 3. So today we will discuss about the second order linear differential equation, because in the last lectures we have developed the theory to solve first order linear and the non-linear differential equation. So in this lecture we are going to start moving further to the second order linear differential equation. So lecture 3. So today we will discuss a second order linear differential equation. So I write the linear differential equation as d square y over dx square plus a1x dy by dx plus a2x a2x y yx is equal to 0. So here I am talking about homogeneous form. So this is the homogeneous. Now I am defining this one in where my x belongs to some interval. So this interval I just take as an open interval between alpha and beta. So I assume that Ax is not equal to 0. So I divide by a naught 0. So this equation reduced to a1x over a naught x dy by dx plus a2x over a naught x yx equal to 0. So I just make it give a new name. So this equation I can write as d square y over dx square plus, so I give the new name to this one. So that is px dy by dx plus qx y equal to 0. So this is my equation, I call it 1a. So in this case I assume that, so this equation has solution if my px and qx are continuous in the given domain, that is my x belongs to open interval alpha beta. So now, so this equation, if we choose some initial condition y at x naught is equal to y naught and y dash at x naught is equal to y naught dash, then so I call it 1b, then the initial value problem, that is 1a and 1b, has unique solution in the given domain, that is between alpha and beta, and if we choose homogeneous initial condition that is y at x naught equal to 0 and y dash at x naught is equal to 0, then it has, then this equation has solution which is identically equal to 0. It means that the solution yx equal to 0 is the only solution in that case. Now, so the equation 1a, so now I introduce a operator, differential operator. Now the equation 1 which we have written like this one, dx square plus px dy by dx plus qx yx equal to 0. So this one I can write as, I define the operator L is equal to y operating on x. So I put it like this one, d square over dx square plus px d by dx plus qx, and then put this one on x. So in this case we define that L is equal to d square over dx square plus px d over dx plus qx. So what is this? It is a function which is applying on a function, because here I am applying on a yx, so this is yx, so this one I am applying on the yx, and the solution whatever the function I am getting, that is also a function. So in this case I can say that this is a function applying on a function. So applying on a function. So this is called differential operator. So differential operator, actually operator is the extension of the functions, because the function we apply on a variable x, in this case we are applying this operator on a function, and the result is also a function. So this operator is the extension of the function. So we define this L. So for example, if I apply L on, so suppose I take L is equal to d square over dx square plus d by dx plus 2 qx. So I take this function, this operator, and I apply on sin x. So this will be, again I am applying on a function, so this is my operator and I am applying on this function. So what I will get, to find out the value, I will put this one here on the sin x plus d by dx on sin x plus 2 qx on sin x. So in this case, okay, so what I do is, so this qx I have taken 2, so this qx will vanish from here, and this will be 2 sin x. So if I take the derivative of this, the derivative sign is cos, and again it is minus, so it will be minus sin x plus cos x plus 2 sin x, and which gives me that sin x plus cos x. So this is the result by applying this operator on the function sin x, and the result is coming sin x plus cos x. So this is an operator operating on a function, and the resultant is also a function. Similarly, I can apply L on, suppose I apply on x square. So putting the same one, I will get d square over dx square on the x square plus d by dx on x square plus 2, and that is x square. So after doing the calculation, I am taking the derivative of x square, so 2x, and taking the derivative again, so it will be 2 plus 2x plus 2x square. So that is again the function. So in this case, that L whatever we are defining here, it is called the differential operator. We define little bit, move further, and we will define that the operator I have defined, that is L, is a linear differential operator. So, what do you mean by the linear differential operator? So, linear differential operator is that if it satisfy, so it is called if it satisfy the following properties. So, what is that property? So, P1, the first property I am defining. So, that is called that if Yx is one of the function is one of the function we are defining by y, then if I define a Cyx, then L of Cyx will be equal to C of Lyx. So, this is the function I have defined my L here, and now I do the scalar multiplication of Yx and operating the same function, then I should get this one. So, this is very easily we can verify that L of Cyx is equal to d square over dx square over Cyx plus Px. So, I am taking the same differential operator which we have defined on the equation 1a. So, d by dx it is Cyx plus Qx, and this will become Cyx. Now, it is a constant. So, I can take this constant common from here, and then it becomes d square Yx by dx square plus Px d by dx and Qx Yx. Here is the Yx. So, this is again the same as L C of L of Yx. So, the first property is satisfied. Then we define the second property. So, second property is that the P2, this property 2 is that L of y1 plus y2. So, in this case I have two function y1 and y2, and operating the L on this summation. So, in that case it should be equal to L of y1, that is operating on x, plus L of y2, that is operating on x. So, this one I can also prove very easily. So, we have a operator dx by dx square. So, this is y1x plus y2x plus Px d by dx, it is y1x plus y2x plus Qx, and putting here y1x plus y2x. So, this one we are writing. Now, this is the summation of the functions. So, from here I know that the derivative is a linear operator. So, it can be taken as a separate form. So, it can be written as d square over dx square y1x plus Px d by dx y1x plus Qx y1x. So, I can separate this one and can write like this one, and the another one is d square over dx square y2x plus Px d y2x over dx plus Qx and y2x. So, this is also I can separate, and from here, so after doing this one, from here I can say that my L of y1 plus y2 applying on this one, they are the same as L of y1x plus L of y2x. This is applying. So, after doing this one, we can say that if this is satisfied, then I can say that L is a linear differential operator. Okay. So, this is a linear differential operator. So, the example I have taken, for example, I have taken my L is equal to d square over dx square plus 2 d by dx plus 3, that is a linear differential operator, because if I apply on this one, it is a linear. Another one, I take d square over dx square plus sin x d over dx whole square plus 4. So, I take this one. So, in this case I have a square root of the derivative. So, I can prove that this is not a linear operator. So, not a linear operator, because from here I can show you that L of y1 plus y2x is not equal to L of y1x plus L of y2x. So, it can be proved very easily. So, that is you can do as a homework. Then, so in this, now after doing this one, so we know that this is a linear operator. Now, so the question is that why we are doing this one, we are defining the linear operator, because our main purpose is to solve the differential equation. So, to develop the solutions, we need some theory that how the operator works on a operate on a function, and which function we can say, which operator we can say that is a linear operator or non-linear operator. So, now, so I know that this is my second order differential equation. So, so let us take one example. I have very simple differential equation dy by dx square plus plus some constant I want to take. So, I just take 4 dy by dx is equal to 0. So, this is the differential equation I have taken, in which the coefficients are constant. It can be a function of x, but here I am taking this one. So, this equation I want to solve, or I want to solve d square y over dx square minus, in this case I take 5 dy by dx plus 2y equal to 0. So, this one I can take. Now, if I want to solve this equation, I need a solution that is the yx, and we also know that the general solution of second order linear differential equation contains two arbitrary constants. So, my main purpose is to find the general solution for this equation. Now, like this one, this is the my one of the equation, this is another equation, and I want to solve this equation. So, if you see clearly from the equation, I need a function yx such that I do a scalar multiplication with that function, take the derivative, adds in the first equation, then I should get the value 0. In the second one, I should have a function such that this function is multiplied by 2, and then taking the derivative of that function multiply by 5, and then again taking the derivative of that function and adding all these together, it should make 0. So, in this case I should look for the functions which has the derivative of similarity. So, let us go for the functions which have the same derivatives, like I can take a sine function. So, sine function, the derivative of sine function is cos, and then taking the another derivative, it is a minus sine x. So, in this case sine x, but we have to take the two derivatives to get the same function. Then, so it means the sine x will not the function we are looking for. Then I can go for the polynomials, but in the polynomials we know that whenever you take the derivative, its degree will reduce by 1. So, that is also not going to fit for this type of equation. Then we come across the exponential function. So, like I take the exponential function like e lambda x. So, in this case I know that the exponential function has the derivative of the same form. So, if I take the derivative of exponential function, it will be lambda e lambda x, again where lambda is any scalar I am taking. I taking the I take the second derivative of e raised to power lambda x, and from here I get lambda square e lambda x. So, this function has the same derivative, and whenever we are taking the derivative, this function is multiplied by the value of lambda. It means this function can be the solution of this equation. So, we take that, let us I solve this equation, I call it second one. So, let e raised to power lambda x is a solution of equation number 2. So, if it is the solution of the equation number 2, it should satisfy that equation. So, in that case, so this is my y x I am taking, y x is equal to this. So, I should have d square over dx square e lambda x plus 5 d by dx e lambda x plus 2 e lambda x equal to 0. So, in this case I take the derivative 2 times. So, I am getting lambda square, I take the derivative 2 times. So, it will be lambda square e lambda x plus 5 lambda e lambda x plus 2 e lambda x equal to 0. Now, so from here I can take the e lambda x common, and I will get lambda square plus 5 lambda plus 2. So, in that case this is the remaining part. Now, from here I know that e lambda x is never 0. So, it is the factors, 2 factors multiplied together and giving 0. So, either one of them should be 0. So, in that case I will say that the lambda square plus 5 lambda plus 2 is equal to 0. So, whatever we are getting is called, so this type of thing is called a auxiliary equation. Auxiliary equation associated with the differential equation. So, now if you see clearly that this is the quadratic equation, and the quadratic equation we can solve. So, if I solve this one, I will get the value of lambda 1 and lambda 2. So, the lambda 1 and lambda 2 are the 2 roots of this equation. So, I can go further in that case. So, let I assume that lambda 1 is not equal to lambda 2. So, it means and they are real. So, if I suppose that the lambda 1 and lambda 2 are not equal and they are real, because we can solve this one very easily. So, this will be lambda is equal to minus 5 plus minus b square minus 4 ac. So, this will be 8 divided by 2. So, whatever I am getting here is minus 5 plus minus, so it will be 17 under root 2. So, these are the fractions we are getting. So, so these are the reals, and lambda 1 and lambda 2 are not the same. So, in that case I will get 2 solution, that is called lambda 1 x and lambda 2 x. So, these are the two solution I am getting. So, I will call it, this is the first one y1x, and this I will call it as a y2x. So, these are the solution, two solution I will get whenever I will come across such type of equation which has a quadratic as a auxiliary equation. So, now I have a two solution, but here this differential equation I want a one solution or maybe two solution. So, in this case I have two solution. Now, I want to write the general solution of this equation. So, the general solution yx will be equal to C1e lambda 1 x plus C2e lambda 2 x, because I told you that this is a second order linear differential equation, and in this differential equation the two arbitrary constant will appear. So, C1 and C2 are the two arbitrary constants, provided, so this is true provided the solution y1x and y2x are linearly independent. So, what is the linearly in DPE? So, that condition is there, that my solution y1x and y2x should be linearly independent. Linearly independent means that, so let us introduce the concept of linearly independent. So, we must have seen this type of concept, linearly dependence or linearly independence, in the case of vectors, where we have a vectors that contain the numerics, but here we are dealing with the function. So, I want to discuss that how the functions can be told that whether they are linearly independent or dependent. So, let us do this one. So, I have two functions y1x and y2x, and I want to check that whether these are linearly independent. So, that is called Li, or linearly dependent, so that is called LD. So, what do you do? It is the same concept as we are doing for the vectors. Take the linear combination. So, let I take some constants, I should take C1 y1x plus C2 y2x is equal to 0. So, this is the linear combination I take, that is the criteria to check that whether the functions whether the vectors are linearly independent or not. We take the linear combination and put equal to 0. So, this is the first equation. So, I call it equation number 3. Now, I have two variables C1 and C2, this one I want to find. So, to find out this one I need another equation also, because we know that we have two variables to find out, and then to find out the solution we need the two equations. So, what I do is that, and I know that y1x and y2x is the solution of the linear differential equation. So, these functions are differentiable function. So, what I do is that I take the derivative of the equation 3 with respect to x. So, when I take this one, so I will get this one equal to 0. So, this is my equation now. Now, this is the system. So, I can write that system as y1x, y2x, y1 dash x and y2 dash x, and this one I can add as C1 and C2, this is equal to 0 0. So, if you see it clearly that this is a system 2 by 2 system, and this I can write as A C is equal to 0. So, this is the homogeneous system of equations, and we know that this system has, so this system has two ways: unique solution and infinite many solutions. So, unique solution will be in this case if A is non-singular. So, if the A is non-singular, I can take its inverse, and in that case my C will be A inverse 0 and that will be 0. So, for the unique solution we know that this is the only trivial solution. So, we call it trivial solution, and if A is equal to 0, then in that case we may have the infinite many solutions. So, here also, so this is the case I am taking. Now, to solve this one, so this is my matrix. So, I want to check that I define this matrix by some. So, I take this matrix and want to find its determinant y1 dash x and y2 dash x, and take the determinant. So, determinant will be y1 y2 dash minus y2 y1 dash. So, this is the determinant. So, we call this determinant as with a new name that we represent by w, and that is equal to x, and also we call it sometime w. So, this one is w. So, we call it w y1 y2 x, and this w, which is a determinant of the corresponding matrix, is called the Wronskian of the. So, this is called Wronskian. So, this is called the Wronskian, this factor. So, in this case my Wronskians is equal to y1 y2 dash minus y1 dash y2. So, that is the determinant of this matrix made up of the functions. So, now, so I will say that if Wx, the Wronskians, is not equal to 0, in that case I will have unique solution. So, unique solution means trivial solution, and in that case I will get C1 is equal to 0 and C2 is equal to 0. So, in that case I can say that my function y1x and y2x are linearly independent. So, they are linearly independent. Now, there is another theory that if Wronskian is 0 at even a single point for any x is equal to x naught, that x naught belongs to the domain in which the differential equation is defined, then in that case then in that case then the Wronskian f x is also equal to 0 for all values of x belongs to alpha beta. So, in that case the Wronskians will be 0 for all value of x alpha beta in the given domain, and in that case I will say that y1x and y2x are linearly dependent. So, this is the related to the Wronskian. So, for example, suppose I take two functions ex and e to the power 2x, and just I want to check whether these two functions are linearly independent or dependent. So, what I do is that I take the linear combination C1. So, this I will take C1 Ex plus C2 e to the power 2x equal to 0, and then I take the derivative because it is the differential function. So, I take C1 e to the power x plus 2 times C2 e to the power 2x equal to 0. So, this is the equation we get. So, from here, so this is the system of two equations. From here I get Ex E2x E2x again Ex, and this is 2 times E2x. So, this is my system C1 and C2. C1 and sorry, it is C1 that is equal to 0 0. So, in that case my Wronskian will be, so that I can write as E of x and E of 2x. This will be, I am taking the determinant of this matrix. So, it will be 2 times of this. So, it will be 3x minus this one E3x, because Ex multiplied by E2x, so E3x. So, this will be E3x, and I know that exponential is never equal to 0. So, in that case I can say that my function y1x Ex and y2x E2x are linearly independent. So, here we are able to show that these two functions are linearly independent. But sometime it happens, because we are dealing with the second order differential equation, but when we go for the higher order, in that case we can have a 2, 3, 4, more than 4 functions as a solution of the linear equation, and to check that whether the functions are linearly independent dependent, the matrix involved has a lot of functions. So, in that case what we do is that sometimes it is very difficult to solve that matrix. So, we put some value of x in that to make the matrix simpler, and in that case we generally put x equal to 0, and then we see that whether the determinant of the matrix after putting x equal to 0 has the determinant 0 or non-zero. So, in that case if the value is 0, then from there we conclude that the given functions are linearly dependent. So, now I want to take some another function. So, for example, I take some other function. So, before that I just define one theorem that let Px and Qx be continuous in the interval that is given to me, that is alpha x beta, and let y1x and y2x are two solution of equation 1a, the equation 1a that we have started with. So, which contains the Px and Qx 1a, then the Wronskian is either identically 0 or it never 0 for x belongs to the domain alpha beta. So, that is a very strong results, that even if we are able to check, because it is very difficult to check that it is never 0 for any value of x, because if I put a value of x and it comes 0, then I have to apply this formula for all the x, and which is impossible. So, this is a very strong statement regarding the, so so this is a theorem. So before that theorem I just check, so I just give you the proof, because I know that I have two functions y1 and y2. So I know that my Wronskian will be y1 y2 dash minus y1 dash y2. So I am applying the, satisfying this one, I try to prove this one. So let my Wronskian is made up of y1 y2 dash minus y1 dash y2. So this one I have taken. Now I take the derivative of my Wronskian. So this will be y1 y2 dash 2 times plus y1 dash y2 dash. So this is the derivative of this one minus the derivative of this one. So this will be y1 dash y2 dash plus y1 double dash y2 dash. So this will, so if you see this one, it will cancel out. So from here I will get y1 y2 dash minus y1 dash y2, and I know that from my, because this y1 and y2 are the solution of the equation. So I know that y1 double dash plus, from here I just want to tell you that y dash sometime also can be written as dy by dx, this one. So to make it easier to write, we also write like this one. So here I am writing y1 dash, then my px y1 dash plus qx y1 equal to 0, because y1 is the solution of the equation, this one. So from here I can write my y1 double dash will be minus of px y1 dash plus qx y1. Similarly, I have my y2, because y2 is also the solution. So y2 can be written as minus of px y2 dash plus qx y2, this one. So substituting this value in the above equation, so this equation I am substituting. So from here I can write my wx can be written as y1, and this is a minus p. So now I am, sometime to make the things easier, we can write px as p and qx is q. So I can write just as, I am writing this one as minus p y2 dash plus q, sorry, this is a minus, so it will be minus sign also. So this is minus q y2, so this is minus y1, so this is again it will be minus p y1 dash minus q y1 into y2. So if you see this clearly, from here I will get minus of p y1 y2 dash minus q y1 y2, it will be plus p y1 dash y2, and from here it will be plus q y1 and y2, and this will cancel out and we left with this one. So I take the common factor p, and then I can write as y1 dash y2 minus y1 y2 dash, or I can write it as minus of p y1 y2 dash minus y1 dash y2, and if you see clearly then it becomes minus p, and this is what again the Wronskian. So that is my Wronskian we have started with. So now from here I can say that my Wronskian satisfy this differential equation, and what is this? It is the first order differential equation. So I have this differential equation. So that is the first order differential equation we have already solved, that is a linear. Now in this case, So, what we have now, this is always true that the Wronskian always satisfy whenever we put the Wronskian in the differential equation, we come up with the first order linear differential equation satisfied by the Wronskian. So, this equation I call it a W, Wronskian's equation. Now, suppose for some value of x is equal to x naught, my Wronskian is 0, because whenever we want to find out the determinant and suppose we are dealing with so many functions, then the determinant, whatever the determinant is coming, that is a combination of the function, and from there we are unable to say that whether that is going to be a 0 or non-zero for all value of x. So, what we do that we just put the some value of x there. So, I put the value of x naught, and after putting this value of x naught, I found that my Wronskians is 0. So, what will happen in that case? Can I say that this Wronskians will be 0 forever? So, let us this Wronskian is 0 for some value of x, then if you see this one, the combination of these, it become the initial value problem, and we know that the solution is Wronskians, that so that solution we have already know that how to find out. So, my solution in this case will be C e raised to power. So, I know that how to solve this differential equation. So, this will be minus p x dx. So, this equation we know we have solved this one starting from x naught to x. So, in this case, or sometime also we write like this, x naught to x p of s ds. Now, I know that I substitute the initial condition. So, at x naught I have c and then exponential minus. So, this is x naught to x naught my ps ds. So, this integral has a limit starting from x naught to x naught. So, this integral is 0. So, from here I will get that c, this value is equal to c, but it is given that the Wronskian is equal to 0. So, that implies that c is 0. So, if c is 0, from here I can say that my Wronskian is always 0 for all value of x belongs to the interval a b. So, from here by just putting one condition, we are able to see that our Wronskian is 0 forever. So, in that case I can say that Wronskian is 0 for all value of x. So, if this is happening, in that case I will say that the functions are, so for example, I take y1x and y2x are linearly dependent. So, from here I can say that the functions y1 and y2 are linearly dependent. So, from here we have developed a theory that if I have the solutions. So, suppose I have solution, two solution y1x and y2x, and from there I find out my Wronskian, that is also written as this one, and if this Wronskian is 0 equal to 0, then my y1x and y2x are linearly dependent, okay, are linearly dependent. And if this is not equal to 0, in that case y1x and y2x are linearly independent. Okay. One more observation I want to add, that if my Wronskian y1 and y2 x is equal to 0, in that case I will say that my function y1 and y2 x are multiple of one another. That means that in that case I can write one function, say y2x can be written as some constant multiple k y1x. So, y2x can be written as the constant multiple of y1x. Okay. So, this case will happen whenever we have the roots of the characteristic equation, the auxiliary equation are similar or the repeated roots. So, for example, so let us take one example. I want to solve this differential equation. So, y double dash plus y dash minus 6y equal to 0. So, in this case I will that let e raised to power lambda x is the solution, and substituting this one it will give you the lambda square. So, I can write my its auxiliary equation very easily. So, it will be lambda square plus lambda minus 6 e lambda x equal to 0. So, from here, because e lambda x is never equal to 0, so this is never equal to be 0. So, from here my auxiliary equation will be lambda square plus lambda minus 6 equal to 0. So, in that case if I find out the root of this equation, so I will get lambda minus 2 lambda plus 3 equal to 0, because lambda square minus 2 lambda plus 3 lambda lambda and this. So, from here I can find the value of lambda is 2 and minus 3. So, the roots are real roots and distinct roots. So, from here I will get the solution y1x is equal to e raised to power 2 lambda and y2x e raised to power minus 3 lambda. Now, I want to check, suppose I want to check whether this two solution makes the, whether these two solutions are the linearly independent or not. So, in that case if I want to find out its Wronskian, so let us try to find out their Wronskian y1 and y2. So, this will be e 2 lambda e minus 3 lambda, then 2 e 2x lambda, sorry. Okay, sorry. So, in that case I will write it e 2x e minus 3x. Okay. So, the same thing I will do here. So, it will be e 2x e minus 3x. So, taking the derivative of here and taking the derivative here, and if I solve this one, so it will be, if I taking the determinant, so this will be minus of 3 e minus 3x or 2x. So, it will be minus x minus this 2 times again e minus x. So, it will be minus 5 e raised to power minus x, which is never equal to be 0. So, in that case I will say that the y1x is equal to e 2x and y2x is equal to e minus 3x are linearly independent. So, if they are linearly independent, then this set of solution. So, this is a set, I call it e2x and e3x is called fundamental solution of the given differential equation. So, it is the fundamental solution of the given differential equation. Fundamental solution, that any other solution if available, that will be the linear combination of only these two. So, in that case I can write the general solution will be yx is equal to c1 e 2x plus c2 e minus 3x. So, this is my general solution for the given differential equation, and this is a second order equation. So, it should contain two arbitrary constant. So, C1 and C2. So, basically this linearly independent solution that makes the space of functions, if you have some idea about the linear algebra. So, they create the vector space of the function, and these are the bases of that vector space. So, any solution belongs to this category. The solution will be the linear combination of these two solutions. So, that is my general solution. So, today we will stop here, and in the today lecture we have developed little theory about that how we can solve a second order linear differential equation, and then how we can define the fundamental solution, so that we should be able to find the general solution of the second linear differential equation. So, in the next class we will move further and solve some different types of differential equation. Thank you very much.